All right, so for thermodynamics, now that we're finished with the thermochem review, we're going to bring in two new terms, and that's going to be entropy and Gibbs free energy. Okay. Remember we said thermodynamically favored means that it happens without outside intervention. Old word was spontaneous. You'll still see that. But when we say spontaneous, we really mean that it's thermodynamically favored. Can be fast or slow. Okay. For instance, if combusting something is going to be fast, turning a diamond back into graphite, very, very slow. Okay. Second law of thermodynamics says in any spontaneous process, there is always an increase in the entropy of the universe. The entropy of the universe is constant, but the entropy of the universe is increasing. And then the third law of dynamics says the entropy of a perfect crystal at 0 degrees Kelvin is 0. Guess what? Doesn't exist. Theoretical. Yeah. Entropy, of course, is S, is how we I don't know why they got S. E was taken up by energy, so I guess we go with S. Okay. It's a measure of randomness or disorder. An increase in the number of microstates is associated with probability. There are more ways for something to be disorganized than organized, right? Okay. Here's the kicker for delta S is positive for thermodynamically favored. And it's negative for not favored, which is a decrease in disorder or more order. Depends on if you're calling it order or disorder. So if I'm increasing my disorder, then I'm thermodynamically favored, which means I'm becoming less ordered. Okay? It is the thermodynamically favored, whereas enthalpy is a negative value that's thermodynamically favored. Okay? So for entropy, it's positive. Okay, here are some ways that we can increase our entropy. If I'm going from a solid to a liquid to a gas, I'm increasing my entropy because my particles are becoming less ordered. Okay, so I'm increasing my entropy. Entropy also increases when gas molecules escape from the solvent. Okay, when solutions are formed, if I take a solid and I dissolve it into water, I am increasing my entropy because now my particles are less ordered or more disordered because now they're no longer together as a solid, they're in liquids. Okay. My entropy increases when I have a reaction that I form more atoms or molecules when it's formed. Okay. And then also generally with molecular complexity, also KCl versus like Cl2 because there's more electrons. Okay. I have more electrons moving around in the second one than I do the first one. Often increases when they involve increasing number of moles of particles, and then entropy is increasing with increasing temperature. Why? What's happening to the particles? Moving faster, yeah. So here's you an example. Ice cube has less entropy. Okay. There's your visual worth 1,000 words. Guess what that looks like? That should look familiar. I can do the same thing with entropy that I can do with enthalpy, products minus reactants. Okay, so that's not hard. Here we go. Predict the sign of the entropy change for each of the following processes and predict your answer. Justify your answer. So solid sugar is added to water to form sugar water, but it's forming a solution, right? So which one's going to have more, what's the sign of delta S? Positive. Positive, because I am increasing my disorder. And then if I have iodine vapor and it condenses to form crystals, what's going on with delta S? Negative. I'm becoming more ordered, or my entropy is decreasing. Right? All right. How about this one? Which of the following would have the largest increase in entropy between A, B, C, or D? A is right. I heard that, Adam. Yeah, A is right. Yeah, because I'm going from a solid to a gas. Okay. If I look at B, I've got 2 moles of gas forming 2 moles of gas. My entropy would be unchanged, actually, there, for the most part. 2 moles of gas to 2 moles of gas. For K and O3, I'm going solid to a liquid, and although that would be increasing my entropy, not as much as solid to a gas. And then graphite to diamond, or diamond to graphite, either way, that would be unchanged because they're both solids. Okay. Here we go. Calculate the entropy. We'll actually work this one together. Okay. Calculate the entropy for this particular reaction, and I'm giving you the things. Products minus reactants. Notice that our units for entropy are joules per mole K. I'm not sure why the parentheses is in the wrong spot. It should be around the joules. Okay. For joules mole times K. That's fine if you're just outright doing entropy, but you're going to see in a minute when we do enthalpy and entropy together, we got to convert one of those to be the same thing, because I can't have one be joules and one be kilojoules. So we're going to start with products minus reactants. So I've got 2 times 256.6 minus 248.1 plus 1 mole, just so you know it's there, 205.3. That's a 5, not an 8. So my delta S is equal to negative 188.3. Okay? Good? Okay. That's easy because we've done it before. Entropy changes for reversible phase change. That means phase changing at, like basically I'm at phase change. Because Q is equal to delta H at a constant temperature, delta S is equal to the heat transferred over temperature change. So therefore, it's written in your notes already, delta, oops, I didn't say I was going to write. Delta S is equal to delta H over T, negative. Okay? And I believe that's a good place to stop.
Yeah.